Jai Hind students, welcome to my YouTube channel. Students, mind is the chief factor which governs the human body. That is, it is mind which controls the human body, isn't it? So, one should always avoid suggesting to the mind the thoughts of human limitations. What I mean to say is that we are capable of doing anything. We have infinite capabilities. The only thing we need to do is trust our own abilities, and it should be followed by proportionate hard work with dedication and sincerity. Then every dream of ours can be easily fulfilled. So students, with that, let's begin today's session. So today we will be going to discuss the motion of the charged particle under the influence of magnetic field, right? In the previous lecture, we have discussed the motion of the charged particle under the influence of electric field. Here, we will be discussing the motion of the charged particle under the influence of magnetic field. And we will be discussing all the feasible cases, right? So, let's start with case 1. Case 1 is when the charged particles enters the region of magnetic field normally, that is at right angle. That is, the direction of motion of the charged particle is perpendicular to the magnetic field. So, let's consider a charged particle, maybe plus q. Suppose this is a charged particle, plus q, right? Moving with velocity v in the xz plane. This is the z-axis, this is the x-axis, this is z-axis, and this is y-axis. So, let the charge plus q be moving with velocity v in the xz plane, right? Under the influence of perpendicular magnetic field which is directed along y-axis. So again I repeat students, we have considered charge plus q to be moving or to be having velocity v in the horizontal plane. In this case, it is the xz plane. And it is under the influence of perpendicular magnetic field B which is directed along y-axis, right? So, this is the magnetic field, suppose. This is the magnetic field which is perpendicular to the xz plane and is directed along y-axis. This is the magnetic field, right? So, what's the angle between magnetic field and direction of motion of the charged particle? It is 90 degrees. So, this is our case, right? Students, we are aware whenever a moving charged particle is under the influence of magnetic field, then it experiences a magnetic force. And magnetic force, students, it's given by Fm vector, it's equal to Q, V vector, cross B vector. Isn't it? This is the cross product, right? So, Fm, it is perpendicular to both velocity vector as well as the magnetic force is perpendicular to magnetic field vector. By using the properties of the cross product, we can safely conclude that this magnetic force must be perpendicular to both velocity vector as well as magnetic field vector. And the direction of this magnetic force, students, is given by right hand thumb rule, isn't it? So, the angle is to measure from V to B. It's like this. The angle is to measure from V to B. So, in that case, if the fingers curl along the direction of measurement of the angle, then the thumb will represent the direction of force vector. It's like this. V to B. It is like this. The angle is measured from velocity vector to magnetic field vector. Like this. It's in the clockwise direction. So, thumb is pointing towards the origin. That is point 2. So, actually, the force would be along this direction. This is the direction of the force, which will be perpendicular to both velocity vector as well as it is perpendicular to both magnetic field vector, right? Now here force can be perpendicular to the velocity vector only if this force makes the charged particle to follow a circular path. Because we are aware, students, whenever force acts on a body perpendicular to its direction of motion, then it must enable the body to move along a circular path. It do not produce any change in the magnitude of its velocity. Instead, it tends to change the direction of motion of the body continuously. And whenever the direction of motion of a body changes continuously, it clearly suggests that it must be following a circular path. Clear, students? Let's take another example. Suppose the charged particle is over here. So its direction of motion is like this. This is the magnetic field. Magnetic field is directed perpendicular to the XZ plane along the y-axis, right? This is the magnetic field. So angle is 90 degree. So let's find out the direction of the magnetic force. So V cross V, it will be like this. So V cross V, it will be like this. So again, the force is pointed along the radius towards the center. This is the magnetic force. It will be perpendicular to both velocity vector as well as it will be perpendicular to the magnetic field vector. Clear, students? Let's take another case. Suppose this is the position of the charged particle at an instant. So this is where the velocity vector would be, right? It is moving in the XZ plane, in the horizontal plane. So the magnetic field is like this. So the angle is V cross V. It is to be measured like this. So again, the thumb is pointing along the radius towards the origin, which is the center. This is where the magnetic force will act. So again, it is perpendicular to both velocity vector as well as it is perpendicular to magnetic field vector. So it is satisfying this condition. So students, I repeat, whenever the charged particle is moving in a direction perpendicular to the magnetic field, then it will experience a magnetic force, the direction of which will be perpendicular to both velocity vector as well as magnetic field vector. And by applying this thumb rule, right hand thumb rule, we can safely conclude that this force F acts along the radius towards the center, which in this case is the origin. So this magnetic force will make the charged particle to follow a circular path, isn't it? And remember, students, whenever the force acts on a body in a direction perpendicular to its direction of motion, then the force always tends to bring about a change in its direction of motion continuously without changing the magnitude of its velocity. So this magnetic force actually provides the necessary centripetal force so as to allow the charged particle to move along a circular path, right? So one thing is for sure, in this case theta is equal to 90 degree. The path followed by the charged particle is of circular nature. It will follow a circular path when theta is equal to 90 degree. Theta is the angle which the direction of motion of the charged particle is making with the magnetic field, right? So therefore, magnetic force Fm, it provides the charged particle Q the necessary centripetal force. So as to make the charged particle to follow a circular path, isn't it? Therefore, mathematically, students, Fm, the magnitude of Fm, it should be equal to Fc. Clear? And suppose the mass of this charged particle under consideration is small m. Then what is the magnitude of the magnetic force? It is Q V vector cross B vector, right? And a body of mass n moving with velocity v in a circular path of radius r, it will experience a centripetal force given by mv square by r. R is the radius of the circular path which the charged particle follows, right? So let's substitute the value. What's the angle between these two? Velocity vector and magnetic field, it is 90 degree, right? So sin 90 is 1. So QVB sin 90 is equal to mv square by r, right? Sin 90 is 1. This v get cancelled. So rearranging the terms, what we get is r is equal to mv divided by qb. So students, this is an important relationship and this is an important expression for the radius of the circular path which the charged particle follows under the influence of perpendicular magnetic field, right? This is the formula which we'll be using directly while solving numericals based on this topic. Clear, students? So this is one of the important expressions. So this is the expression for the radius of the circular path which the charged particle follows. Now expression for the time period. Students, time period, as you are aware, it is the time taken by the charged particle to complete one revolution, right? Suppose the charged particle starts from this point, so it will take a particular time so as to complete one revolution. So that time taken by the charged particle to complete one revolution is known as its time period. So let's find out the expression for the time period. So time period t, it would be equal to distance over speed, isn't it? So the distance during one complete revolution would be 2 pi r, and it is covering this distance with speed v. The magnitude of the velocity, which is speed, will remain constant. It is the direction of motion that changes continuously, right? So let's substitute this value of r over here. So what do you get is 2 pi by v, and substitute this value of r over here. So mv divided by qv. So time period would be v get cancelled. So what do you get? 2 pi m divided by qv. So this is another very important expression for time period. And students, concentrate on this particular expression, right? T is independent of the radius of the circular path as well as it is independent of the velocity of the charged particle. So the time taken by the charged particle to complete one revolution is independent of both radius of the circular path as well as the velocity of the charged particle. Clear? What it suggests is whether the charged particle follows a circular path of smaller radius or it follows a circular path of larger radius. In all this scenario, the time taken by the charged particle to complete one revolution under the influence of given perpendicular magnetic field would be constant, as it is independent of both v as well as r. Actually, the theoretical explanation lies in the fact that now as the radius increases, the length of the circular path will also increase, but the magnitude of velocity of the charged particle will also increase with the increase in the radius of the circular path. So that the ratio r by v, that remains constant, and accordingly the time period remains constant. Is it clear, students? So this is a key point, right? What about the linear frequency then? The total number of revolutions completed by the charged particle in 1 second, that will be known as its frequency. So what will be the frequency then? Frequency, as you are aware, it is reciprocal of time period, isn't it? So simply it will be given by qb divided by 2 pi m. So this is the expression for the frequency of the charged particle, right? And then there comes angular frequency. Now angular frequency, you are aware, students, it's given by 2 pi by capital T. Reciprocal of time period, that is linear frequency, just now we have discussed 2 pi nu. Therefore, substitute this value of nu over here, 2 pi get cancelled, so we will be left with qb divided by m. So this is the expression for the angular frequency, right? So I hope you have understood this particular article. So students, the main conclusion: whenever a charged particle enters a region of uniform magnetic field in which its direction of motion is perpendicular to the magnetic field, then it will always tend to follow a circular path. And the radius of that circular path would be given by mv by qb. The time period would be given by 2 pi m by qb. The frequency would be given by qb by 2 pi m. And the angular frequency would be given by qb by m. Right, students? So, we are over with case 1. Clear? Now let's discuss case 2. Case 2 is, students, when the charged particle, its direction of motion is inclined. It is inclined. That is, it is inclined. The velocity vector is inclined at an angle theta. It is inclined at an angle theta with the direction of the magnetic field. So here, theta neither makes an angle of 0 degree, nor 180 degree, nor 90 degree. It lies between 0 and 90 degree. So let's see what type of path will the charged particle follow in this case. Okay students, in this particular case, we have assumed the directional motion of the charged particle, that is the velocity vector, is making an angle theta with the direction of the magnetic field, right? So this is the case. This is the directional motion of the charged particle and it is making an angle theta with the direction of the magnetic field, right? So what to do is, let me draw this diagram over here. This is suppose the charged particle, right? This is the direction of the magnetic field and this is the velocity vector. Now velocity vector is inclined at an angle theta with the direction of the magnetic field. What we can do over here is, we can resolve the velocity vector into two perpendicular components. One component which will be along the direction of the magnetic field, that will be v cos theta. No doubt regarding this. And students, the other component, it will lie in the horizontal plane perpendicular to the direction of the magnetic field. And that component is known as the normal component of velocity of the charged particle. And it will be v sin theta. So this is the other component, right? This will be the other component. So this is the normal component and it will be v sin theta. So Vn, it stands for the normal component of velocity. Normal component of velocity. Normal component of velocity means Vn is perpendicular to the magnetic field. Am I clear? So Vn will lie in the xz plane. Clear students? This is the xz plane and this is the y-axis. So here, this is the horizontal plane, this is the y-axis along which magnetic field is directed. So if direction of motion is like this, making an angle theta with the direction of the magnetic field, then v cos theta component of the charged particle is along the direction of the magnetic field, while v sin theta component, that will lie in the xz plane, which will be perpendicular to the magnetic field, right? So if I show it over here, one of the component is v cos theta. This is v cos theta, isn't it? This is v cos theta, and the other component would be v sin theta. This is v cos theta and this is v sin theta, and this is where magnetic field is, right? It is inclined at an angle theta. So what's the angle between these two? 90 degree, right? So now let's consider the contribution of the component of velocity v sin theta. Remember students, v sin theta is the normal component of velocity of the charged particle, which is perpendicular to the direction of the magnetic field. So if you have assumed the magnetic field to be directed along y-axis, then v sin theta component will be in the xz plane, right? Now in the previous article, what we have proved is, in case of normal component or in case of the component of velocity which is perpendicular to the magnetic field, it will make the charged particle to follow a circular path. This we have done in the previous article, isn't it? In the previous case, when theta is considered to be 90 degree. So this v sin theta component, what it will do is, it will make the charged particle to follow a circular path. I'll show it with the help of this diagram. So it will make the charged particle to follow a circular path like this. So as a result, the angle between these two, this is where the magnetic field is also. Okay. Now, as a result, the magnetic force experienced by the charged particle under the influence of magnetic field due to its velocity component v sin theta, it will be again directed along this direction, isn't it? This is the magnetic force. Clear students? So here you can easily check that the magnetic force is perpendicular to both V sin theta as well as the magnetic field. So therefore, in this case, due to this normal component V sin theta, the charged particle will experience a centripetal force which will make the charged particle to follow a circular path. I am only talking about the contribution of the component V sin theta, right? So consider component V sin theta, right? So in this case, we are aware magnetic force, it will be given by Q V cross V. Here, not the entire velocity, only the normal component of velocity cross V vector, right? And this force, which acts along the radius towards the origin, which is the center, will provide the charged particle the necessary centripetal force. Students, this force Fm is acting perpendicular to V sin theta. Therefore, this force Fm will not result in any change in the magnitude of the normal component of velocity. Instead, what it will do is, it will contribute in changing the direction of motion of the charged particle continuously. What I mean to say is that, obviously, Fm due to V sin theta will make the charged particle to follow a circular path, right? So therefore, it will provide the necessary centripetal force, which is the centripetal force, isn't it? So equating, what you get is Q Vn vector cross V vector, magnitude of it is equal to m V square by r. What is the angle between these two? This is the normal component, this one, this is Vn. What is the angle between Vn and magnetic field? It is 90 degree. So what you get is Q Vn V sin 90, it will be equal to m V square by r. And with what velocity the charged particle will follow the circular path? With Vn, right? This is Vn. This is the normal component. We are considering only and only the normal component, which is V sin theta. So Vn get cancelled. Sin 90 is 1. So R would be equal to m Vn divided by Q. Right? So Vn can be written as V sin theta. Therefore, R is equal to m V sin theta divided by QV. So this is the expression for the radius of the circular path which the charged particle will follow due to the component V sin theta. Clear, students? Now what about the time period? Time period, as you are aware, it will be 2 pi r and it is covering the circular path with speed of Vn. So if you substitute this value, 2 pi divided by Vn is V sin theta, R is mV sin theta divided by Qb. So V sin theta get cancelled out. So we will be left with 2 pi m divided by Qb. So we get the same expression for the time period as was obtained in the previous case, right? So as we have discussed earlier also, time period is independent of both radius as well as the velocity of the charged particle. So time period will remain constant, right? So students, what we have discussed is, in case the direction of motion or the velocity vector of a charged particle makes an angle theta with the direction of the magnetic field, then we have resolved velocity vector into two components. One, V cos theta along the direction of the magnetic field. The other component, which is the normal component, V sin theta, which is perpendicular to the magnetic field. So here, students, if the magnetic field is assumed to be along y-axis, then the normal component of velocity V sin theta would be lying in the xz plane, isn't it? And we are aware that whenever we consider that velocity component which is perpendicular to the magnetic field, then it experiences a magnetic force which is of centripetal nature. So this component V sin theta will make the charged particle to experience a centripetal force. As a result of which, it will tend to follow a circular path of radius this, and this will be the time period. Right? This is regarding the contribution of the component of velocity V sin theta. But students, this is not the end of the article. We are left with the contribution of the velocity component V cos theta. right? So what about this v cos theta? Now remember students, this charged particle will experience a force only in the horizontal plane due to this component. It won't experience any force along the y-axis because along the direction of the magnetic field, if the charged particle is having any velocity vector, then it won't experience any magnetic force, right? So this component v cos theta will make the charged particle to move linear distance along the direction of the magnetic field in uniform motion. Look students, along y-axis there is no force acting. Therefore, acceleration along y-axis is 0. Therefore, along y-axis the motion is uniform. So v cos theta component will make the charged particle to follow a linear distance along the direction of the magnetic field. Clear? So this is the key point. So contribution of v cos theta, right? So contribution of component v cos theta. It will make the charged particle to follow a linear path, right? To follow a linear path along the direction of the magnetic field in uniform motion. Uniform motion means with constant speed. Clear students? So again I repeat students, then we will discuss the collective contribution, collective result of these two, right? So the normal component v sin theta, it will make the charged particle to follow a circular path, right? The component v cos theta, that will make the charged particle to follow a linear distance in uniform motion along the direction of the magnetic field. So can you imagine the charged particle is having both the components v cos theta and v sin theta. So what will be the collective result? What will be the collective effect on the charged particle? It needs to follow a circular path as well as it needs to follow linear distance along the direction of the magnetic field. So combine these two. So as a result, what happens is, students, this is suppose y-axis. In this direction, magnetic field is assumed to be directed, right? So the charged particle will follow both circular path as well as it will tend to move some linear distance along the direction of the magnetic field. So in order to satisfy both the conditions, what happens is charged particle will tend to follow a helical path like this. Helical path means, students, you have heard about helical spring. Actually, you must have seen helical spring, isn't it? The charged particle in this case will follow a path, just as in the case of a helical spring. So it will follow both circular path, and during each revolution, it will also cover some linear distance along the vertical direction, that is along y-axis, which is along the direction of the magnetic field. So it will tend to follow a helical path like this. During each revolution, it will follow a certain linear distance along the direction of the magnetic field. So students, ultimate result of both these components is that the charged particle will tend to follow a helical path. Is it clear, students? So I'll explain. I'll draw the diagram. I'll draw the relevant diagram actually. Suppose this is x-axis, this is z-axis, this is z-axis, and this is y-axis. This is the direction of the magnetic field, right? So charged particle, what happens is v sin theta component, it will make the charged particle follow a circular path. V cos theta component, that will make the charged particle follow a path, linear distance, linear path along y-axis, that is along the direction of the magnetic field. So what happens is, it will be like this. Look, it will follow a circular path as well as it will tend to follow a linear distance along y-axis. So ultimate result is that the charged particle will keep on following circular path as well as it will keep on covering some linear distance along the direction of the magnetic field. So as a result, the nature of path of the charged particle must be helical. So it is like this. Right, students? This is the case. So look, during each, this is suppose t equals to 0. Now at this point, it will complete one revolution. And the time taken by the charged particle to complete one revolution, that is known as time period, isn't it? Then again, it will complete one revolution. Again, it will come over here, completing one revolution. So again, the same time capital T will elapse. Again, it will follow the circular path and it will come over here. So it will be t equals to 3t. So what I mean to say is that during each period capital T, it will cover one revolution as well as it will cover same constant linear distance along the direction of the magnetic field. Right? So this distance must be equal. This distance I am talking about. Suppose let it represented by A. So this distance will remain constant. This is it, students. Right? This distance covered by the charged particle along the direction of the magnetic field with uniform speed v cos theta during time period capital T is constant. And students, this distance A is known as pitch. It is known as pitch. P-I-T-C-H. It is known as pitch. So how to define pitch then? Pitch is the linear distance covered by the charged particle along the direction of the magnetic field in the time during which it completes one revolution. Is that clear, students? Now let's find out the expression for the pitch. Pitch are considered to be A. Now as I stated, it will follow a linear distance, linear path along the direction of the magnetic field in uniform motion. In uniform motion, the speed will be constant. So v cos theta will be constant, right? So in linear motion, distance is speed multiplied by time. With what speed it covers this distance along y-axis? With speed of v cos theta. And in what time it covers this distance along the direction of the magnetic field? In time capital T. So this is the formula for the pitch. Pitch is the distance covered by the charged particle along the direction of the magnetic field in the time during which it completes one revolution. Right? So pitch would be given by v cos theta multiplied by time period. Substitute this value of t over here. What do you get? 2 pi m divided by qb. So students, this is the formula for the pitch. Clear? So we are over with these two articles, these two cases. So again I repeat, students. In case charged particle, its direction of motion is inclined at an angle theta with the direction of the magnetic field, then the velocity vector can be resolved into two components. V cos theta, it is the component along the direction of the magnetic field. This component will make the charged particle to move linearly with constant speed of v cos theta along the direction of the magnetic field. While the other component v sin theta, which is perpendicular to the magnetic field and is known as a normal component, will make the charged particle to follow a circular path. So what will be the overall result then? The overall result will be that the charged particle will follow both circular path as well as it will keep on moving along the direction of the magnetic field. Right? So as a result, it must follow a helical path. This is the helical path I am talking about. This is the helical path. Like this. During each revolution, the charged particle will keep on covering some linear distance along the direction of the magnetic field. and that linear distance covered by the charged particle along the direction of the magnetic field in the time during which it completes one revolution is known as the pitch. Clear, students? Okay. So, case 3 and case 4, they are left. Now we will discuss the path followed by a charged particle when the charged particle is moving either along the direction of the magnetic field or in a direction opposite to that of the magnetic field. Right? So, let's discuss case 3 and case 4. Case 3, when theta is equal to 0 degree. That is, this is the direction of the magnetic field, and charged particle, it is also moving along this direction. So what is the angle between V vector and B vector? It is 0 degree. Now look over here. Magnetic force, we are aware, it is given by Q, V vector cross B vector. So what's the angle between these two? 0 degree. So in magnitude, it would be equal to Q VB sine 0. Sine 0 is 0, so it will be 0. So students, in case the charged particle moves along the direction of the magnetic field, then it won't experience any magnetic force. If it won't experience any magnetic force, then what happens? Acceleration will be 0. So its direction of motion will remain unaffected. That is, the charged particle, in the absence of any magnetic force, it will keep on moving along the same initial direction. Its path won't get affected. So this is the case where the path won't get affected. It won't change. So the charged particle will keep on following the same straight path in the absence of any magnetic force. Right, students? So case 3 is also over. Case 4, again the same. Even if case 4. Now, if magnetic field is like this and the charged particle is moving in the opposite direction, so the angle between these two is 180 degree. Now students, sine 180 is also 0. So therefore, in this case also the magnetic force is 0. So whether the charged particle is moving along the direction of the magnetic field or in a direction opposite to that of the magnetic field. So whether the angle is 0 degree or 180 degree between the velocity vector and the magnetic field vector. In both the cases, the charge will not experience any magnetic force. And we are aware, students, in the absence of any magnetic force, the charged particle will keep on moving in uniform motion along the same straight path. So in both the cases, the path of the charged particle won't get affected. Right? So, we are over with all the 4 cases. Just to summarize, in the first case, the charged particle will follow a circular path. It will follow a circular path. In the second case, students, the charged particle will follow a helical path. In the third and fourth case, it will remain unaffected. The path of the particle will remain unaffected. So, we are over with all the cases, right? So, that's it for this particular session. I hope you have understood each and every concept in detail, right? So, do join me in my next lecture. Till then, do take very good care of yourself and stay blessed. Thank you.